The Pacific Ocean is boiling, underwater, silently, and it's about to change everything above the surface. A massive pulse of warm water the size of a continent is moving across the ocean floor right now. Scientists call it a Kelvin wave. When it hits the surface, it could trigger the strongest El Nino in 140 years. We're talking droughts that collapse harvests, storms that slam coasts that almost never flood, and temperatures that could make the next 2 years the hottest in recorded history. We'll follow the science, the warnings, and the real consequences, from the Philippines to India to your own backyard. If you find this worth your time, a like and subscribe helps us keep going. Stay close. We begin now. The Pacific Ocean covers more ground than every continent on Earth combined. That is a fact most people hear and immediately forget. But right now, that size matters more than it ever has. Because something is happening inside that ocean. Something slow, deep, and powerful. And by the time most people notice it, it will already be reshaping the weather across the entire planet. El Nino starts with water. Specifically, with warm water. Picture the equatorial Pacific as a giant bathtub. Normally strong winds blow from east to west across the surface. Those winds push the warm, sun-heated water toward Asia and Australia. The western side of the Pacific sits warm and full. The eastern side, near South America, stays cooler because cold water wells up from the deep to replace what got pushed away. That balance is the system working as designed. Every farmer in the Philippines who plans a rice harvest depends on it. Every meteorologist in California tracking rainfall depends on it. The whole global weather machine leans on this one balance point in the middle of the Pacific. El Nino is what happens when that balance breaks. When the winds weaken, they stop pushing warm water west. The warm water spreads back toward the center and east of the Pacific. Sea surface temperatures in the central equatorial Pacific climb 2, 3, sometimes 4 degrees above normal. That may sound small, but the ocean covers so much space that even 2 degrees of extra heat pumps an enormous amount of energy into the atmosphere above it. That energy has to go somewhere. It rises, it shifts pressure systems, it bends the jet stream, which is the river of fast-moving air that steers storms across continents. Suddenly places that expect dry seasons get slammed with floods. Regions that count on monsoon rains go dry. Weather patterns that billions of people have built their lives around stop working the way they should. Scientists confirmed this connection decades ago. El Nino is one of the most studied climate events on Earth. Forecasters track it using thousands of ocean buoys, satellites and computer models, running around the clock. They know what causes it. They know roughly how it behaves. And right now, in 2026, they are watching something build that has most of them genuinely alarmed. The event forming this year is following a path that looks almost identical to the early stages of the worst El Niños in recorded history. The ocean is warming faster than the models expected. The warning signals appeared months ahead of schedule, and at least one major forecasting agency has placed the odds of a historically extreme event at 100%. The science is clear on this. El Nino does not hit every part of the world the same way. Some regions flood, others burn, some escape almost untouched while their neighbours suffer for years. The outcome depends on where you live, how prepared your country is, and how strong this particular event ends up being. That last part is where scientists still disagree, but they all agree on one thing. The ocean has been storing energy for a long time, and it is getting ready to release it. What that release looks like when it fully arrives is something that keeps forecasters up at night, and the answer starts not at the surface of the ocean, but hundreds of feet below it. Most people think of the ocean as flat, a surface, something you look at. But the ocean has layers, and right now, the most important layer is one you will never see from a beach. Think of the ocean like a massive rechargeable battery. The sun is always charging it. Every day, sunlight hits the surface and pours energy into the top layer of water. But water holds heat differently than air does. Air loses its warmth fast. Water holds on to it. It stores it. It can carry that heat for months, even years, before releasing it back into the atmosphere. The Pacific has been charging. For the past several months, scientists tracking the subsurface temperature of the equatorial Pacific have watched something remarkable. Deep below the surface, hundreds of feet down, water temperatures have been running 6 to 7 degrees above normal. That is an enormous number for the ocean. The Pacific is not a bathtub you can heat up quickly. It takes a massive, sustained input of energy to move those temperatures that far, and yet here we are. Here is why this matters in a way you can picture. Imagine you have a giant sponge soaked with hot water. On the outside, the sponge feels a little warm, but nothing alarming. Then someone squeezes it. All that stored heat comes rushing out at once. The Pacific is that sponge. The warm water has been building in the subsurface. When it finally reaches the surface and spreads across the equatorial Pacific, the atmosphere above it responds immediately and dramatically. Scientists call the stored energy in the subsurface ocean heat content. Right now, the heat content of the Pacific is at one of the highest levels ever recorded in the modern era, confirmed by satellite data and by the network of ocean buoys that measure temperatures at different depths across the entire basin. The heat has to go somewhere. When it reaches the surface, it warms the air above it. That warm, moist air rises fast. It fuels storm systems. It pushes heat into the jet stream. And the jet stream carries those changes thousands of miles away, into places that will never see the Pacific Ocean, but will absolutely feel what is happening inside it. This is how El Nino punches above its weight. The actual warming happens in one part of the world. The consequences land everywhere else. A team of researchers tracking the Pacific subsurface in early 2026 described the heat reservoir as unusually large. Not just the temperature, but the sheer volume of warm water sitting below the surface. The area involved stretches across a distance comparable to crossing the United States from coast to coast and then going another 1,000 miles. That is how much warm water is waiting to surface, and right now something is pushing it up. A pulse. A wave. Moving silently through the dark water, thousands of feet below where any ship sails or any swimmer ever goes. Scientists have a name for it, and once you understand what it does, you will understand why the forecasters watching 2026 look the way they do. Imagine a wave you cannot see. No white caps, no crash on a shoreline, no movement visible from above. Just a slow, powerful surge of warm water travelling through the deep ocean at about 300 miles per day, stretching across the entire Pacific from west to east. Scientists call it a Kelvin wave. It is one of the most important things happening on Earth right now, and almost nobody outside of climate science has ever heard of it. Here is what it actually is. When the trade winds weaken near the equator in the western Pacific, they stop holding the warm surface water in place. A pulse of warm water gets released. That pulse sinks slightly and travels eastward through the subsurface ocean, staying locked to the equator by the rotation of the Earth. It moves like a slow-motion wave through the deep, carrying enormous amounts of heat with it. In early 2026, scientists identified 2 of these pulses moving through the Pacific at the same time. 2 Kelvin waves stacked one after another, each carrying water that was running 6 to 7 degrees above normal at depth. That combination sent alarm through the forecasting community. 1 Kelvin wave can prime El Nino. 2 in rapid succession can supercharge it. Picture it this way. The thermocline is the invisible boundary between warm surface water and cold deep water. Normally it sits relatively shallow in the eastern Pacific. Cold water stays close to the surface there, which keeps things cool. A Kelvin wave acts like a battering ram against that boundary. It pushes the thermocline deeper, forcing the cold water down and allowing the warm water above it to expand and spread. When the thermocline gets pushed deep enough, the cold water can no longer reach the surface. The warm water takes over. Sea surface temperatures rise. El Nino begins to fully express itself. That is exactly what forecasters started seeing in spring 2026. By April, buoys scattered across the equatorial Pacific were registering above normal sea surface temperatures stretching from the central Pacific eastward towards South America. The subsurface heat that had been building for months was beginning to punch through. The Kelvin waves had done their work. Here is the alarming part. Scientists confirmed this is not a theory at this point. The Kelvin waves were real, measured, tracked in real time. The subsurface warming was documented and verified. The thermocline in the eastern Pacific had been pushed down to depths that made a strong El Nino almost certain to develop. But a Kelvin wave alone does not decide how strong El Nino gets. The strength depends on what happens next, specifically on whether the atmosphere responds to the warming ocean or stays quiet. In 2015, when the last record-breaking El Nino formed, the atmosphere responded fast and hard. The warming ocean and the shifting atmosphere locked into a feedback loop. Each one amplified the other. Sea surface temperatures kept rising. The event grew stronger than almost any model had predicted. In 2026, forecasters are watching the atmosphere very closely. Because if it responds the same way it did in 2015, what comes next will be something the world has not seen in over a century. And the first sign that things were already accelerating came from the data NOAA released in May 2026. Models that had predicted neutral conditions through June suddenly showed something very different. 3 months. That is roughly how much time forecasters were caught off guard by in 2026. At the start of this year, La Niña was still active across the Pacific. La Niña is El Niño's opposite. Where El Niño warms the central and eastern Pacific, La Niña cools it. The trade winds strengthen. Cold water surges to the surface. Rainfall shifts. The whole system tilts in the opposite direction. La Niña had been running for over 2 years by January 2026. That is a long event. And the forecast from most major agencies going into the new year was consistent. La Niña would weaken, the Pacific would settle into neutral conditions, and El Nino would be a story for late 2026 at the earliest. Some models suggested it might not arrive in force until 2027. Then February hit. Researchers tracking the subsurface Pacific in February 2026 found the Kelvin waves already surging eastward. The heat content below the surface was rising fast. PAGASA, the National Weather Agency of the Philippines, officially declared La Niña over on March 9th. The Pacific had shifted to neutral in a matter of weeks rather than months. But neutral did not last. By April, the temperature signals in the central Pacific were already tipping into El Nino territory. The Columbia University forecast model placed a 70% chance of El Nino arriving as early as April through June 2026. Just 2 months earlier, the World Meteorological Organization had put the odds of El Nino developing by spring at only 10%. The gap between those two numbers tells you everything about how fast the Pacific moved. For a forecast to swing from 10% to 70% in the span of 8 weeks, something had to accelerate dramatically, and it did. The Kelvin waves moved faster than expected. The trade winds relaxed sooner than modelled. The subsurface heat that had been building for months rushed to the surface ahead of schedule. This matters for everyone, not just meteorologists. When a climate event develops faster than predicted, governments and farmers and emergency managers who are planning around one timeline suddenly have less time to prepare. A late-season El Nino gives growing regions time to adjust their planting schedules. An early arriving El Nino can blindside them. The Philippines had planned for a buffer. Farmers in Luzon and Mindanao were working from seasonal outlooks that still pointed to adequate rainfall through the first half of the year. By the time PAGASA issued its formal El Nino alert in late April, the window for preparation had already shrunk. Australia's Bureau of Meteorology was updating its outlooks monthly, watching the acceleration with concern. India's meteorological department was quietly revising its monsoon forecast downward. The world was catching up to something that had already started. And behind this acceleration was a question that nobody had fully answered yet. Was this just a fast-developing El Nino, one that would peak at moderate strength and fade? Or was the speed itself a sign of something bigger, a system so loaded with stored energy that it was moving faster precisely because there was so much more of it? NOAA's May 2026 forecast update would answer part of that question, but it also raised a new one that made everything more urgent. May 14th, 2026. NOAA's Climate Prediction Center released its monthly El Nino outlook. Normally these updates draw attention from meteorologists, agricultural planners, and government disaster offices. This one drew attention from almost everyone. The previous month's forecast had still shown neutral conditions likely through June. Most of the model ensemble was calm. El Nino was expected, but gradually. The story in April was watch and wait. May's forecast changed that story entirely. The new numbers placed an 82% probability of El Nino conditions developing within the next 2 to 3 months. 96% probability it would persist through the Northern Hemisphere winter, and 66% probability that when it peaked, it would reach strong or very strong intensity. In climate forecasting terms, those are not cautious numbers. They are alarm level numbers. What changed between April and May was the ocean itself. The sea surface temperature anomalies across the central equatorial Pacific had jumped in a matter of weeks. The atmospheric signals that scientists watch alongside ocean temperatures began to respond. Trade winds were weakening, pressure patterns were shifting. The feedback loop that drives El Nino was starting to engage. Scientists at NOAA described the acceleration as faster than their models had anticipated. The models had expected the ocean to warm gradually over the spring. Instead, the warm water from the subsurface pushed to the surface faster and spread wider than the previous month's runs had shown. Picture it like a dam slowly filling with water for months. The models were predicting the dam would overflow sometime in late summer. Instead, the water level jumped 6 feet in a single week. The overflow had already begun. For the public, the update meant one thing above all others: El Nino was happening. The debate had shifted from whether it would arrive to how large it would grow. NOAA's team was careful to explain the uncertainty. Stronger events do not automatically guarantee more severe impacts, they noted. Strength increases the probability of specific outcomes, like below normal rainfall in Southeast Asia and above normal precipitation in the southern United States. But geography and local conditions still shape how those probabilities play out on the ground. That caveat mattered. But for countries already watching their rainfall gauges, it offered limited comfort. There was another number in the May update that quietly unsettled researchers who read closely. NOAA put the odds of a very strong event, defined as sea surface temperatures rising 2 degrees Celsius above average across the central Pacific, at 23% for October through December 2026. A separate National Weather Service model put the odds of a Super El Nino forming by November at 37%. 37% may not sound alarming, but when you consider how rare Super El Nino events are, and how much destruction the last one caused in 2015 and 2016, 37% is a number that demands serious attention. And NOAA was the conservative voice in the room, because the European model had already gone somewhere far more extreme, a forecast that climate scientists had never seen issued at that confidence level before. 2 degrees. On a regular thermometer, 2 degrees is almost nothing. You would not feel the difference stepping outside. A sick person running 2 degrees above normal temperature would not even be sent home from school. But 2 degrees of warming spread across millions of square miles of ocean is something else entirely. The ocean is massive. When you heat even a small fraction of it above normal, the amount of extra energy involved becomes almost impossible to picture. Scientists put it this way: the total heat stored in the top layer of the ocean is hundreds of times greater than all the heat stored in the entire atmosphere. Moving that system by 2 degrees is like pressing the entire atmosphere's energy input several times over. That energy does not stay in the water. It moves. Warm ocean water evaporates faster than cool water. That extra evaporation pumps huge amounts of water vapor into the atmosphere. Water vapor is the atmosphere's fuel. More of it means bigger storms, more intense rainfall in some regions, and stronger winds. The atmosphere responds to what the ocean gives it. But the warming does not hit the whole planet equally. El Nino reshapes the atmosphere in a very specific pattern. The warm water in the central Pacific creates a region of rising air and intense rainfall right there, near the equator. But that rising air has to come down somewhere. It descends over other parts of the world, compressing the atmosphere and suppressing rainfall. That is why a warming in the middle of the Pacific can cause a drought in Australia, 3,000 miles away. The physics are connected. Scientists confirmed decades ago that the link between El Nino and distant weather changes, a pattern they call teleconnection, is real and measurable. During strong events, teleconnections reach all the way to Africa, Europe, and the Americas. The fingerprint of El Nino shows up in crop data, river levels, wildfire maps, and hospital records across dozens of countries. The monsoon is one of the most critical pressure points. Asia's monsoon system delivers most of the annual rainfall that 600 million farmers depend on across India, Southeast Asia, and East Africa. It runs on a temperature difference between the land and the ocean. When El Nino warms the ocean more than usual, it disrupts that temperature contrast. The monsoon weakens. Rains arrive late or fall short. In a mild El Nino year, the shortfall might be manageable. In a strong event, it can be catastrophic. India experienced below-average monsoons during the 2015 to 2016 El Nino. Parts of Southeast Asia went months without meaningful rainfall. Reservoir levels dropped. Power generation from hydroelectric dams fell. Crops failed across multiple growing seasons. 2 degrees of ocean warming did all of that. Now imagine the warming reaches 3 degrees. Scientists say that is within range for 2026's event. That is territory the world has not entered in well over a century. The ocean is the engine. But the consequences land on people who may never have heard of a Kelvin wave or a thermocline. They just know their crops are dying and the rain stopped coming. Understanding why this happens requires going deeper into the ocean. Literally. Close your eyes and picture a wall of air. Not a wall you can see. A wall made of wind running along the equator for thousands of miles, blowing steadily from east to west day after day, year after year. This wall has been there for as long as humans have sailed the Pacific. Sailors called these winds the trade winds, because they were so reliable that merchant ships used them to cross the ocean on schedule. Those winds are not just useful for ships. They are essential for the stability of the entire climate system. Here is what the trade winds do. They blow warm surface water westward across the Pacific. All that sun-heated water gets pushed toward Asia and Australia, piling up on the western side of the ocean. The sea level on the western side of the Pacific is actually about 2 feet higher than on the eastern side, because so much water gets pushed there. Scientists have confirmed this. The trade winds are powerful enough to create a measurable difference in sea level across an ocean. On the eastern side, near South America, the surface water that got pushed away gets replaced. Cold water rises up from deep below to fill the gap. That cold water makes the eastern Pacific cooler and drier. It supports unique marine ecosystems, and it keeps the whole temperature gradient across the Pacific in balance. The trade winds are the lock that holds the system together. When they weaken, even slightly, that lock starts to open. Warm water stops being pushed so aggressively to the west. It begins to spread back toward the center of the Pacific. The cold water upwelling in the east slows down. Sea surface temperatures in the central and eastern Pacific start to rise. The atmosphere above the warming water responds, and the atmospheric response feeds back into the winds. Weaker winds allow more warming. More warming disrupts the pressure systems that drive the winds. The pressure disruption weakens the winds further. The system feeds on itself. This feedback loop is the engine of El Nino, and once it gets going, it is very hard to stop until the cycle runs its course naturally, usually over the span of 9 to 12 months. In 2026, trade wind weakening was confirmed by multiple monitoring networks across the Pacific as early as spring. The signal was clear. Forecasters watching the wind data saw the lock beginning to open months before most people knew an event was forming. There was another signal layered on top of the wind data. Near the equator in the Western Pacific, a specific type of wind event was showing up in the data. Scientists call them westerly wind bursts, short, intense pulses of wind blowing east rather than west. These bursts act like an accelerant. They push extra warm water eastward. They enhance the Kelvin waves already moving through the subsurface. In early 2026, westerly wind bursts were appearing in the data with increasing frequency. Each one added more energy to the building event. The winds that normally hold the Pacific in place were not just weakening. They were actively helping push the system in the wrong direction. And beneath all of this, there was a physical boundary in the ocean that was about to get pushed to a depth it had not reached in a very long time. Somewhere beneath your feet right now, if you are standing on the equatorial Pacific, there is a wall. You cannot see it. You cannot touch it. But every marine creature that lives in the equatorial Pacific knows it is there. Every climate model in the world accounts for it. And right now, in 2026, it is being pushed downward by forces that have scientists paying close attention. This wall is called the thermocline. It is the boundary between two completely different worlds inside the ocean. Above the thermocline, the water is warm. Sunlight heats it. Winds mix it. Currents carry it around. Below the thermocline, the water is cold, dense, dark, almost completely still. The two layers sit one on top of the other without mixing, like oil and water in a bottle. In the eastern equatorial Pacific, the thermocline normally sits close to the surface, sometimes only 150 to 200 feet down. That is shallow. Cold water is right there, available to well up and keep surface temperatures cool. That shallow thermocline is one of the main reasons the eastern Pacific stays so much cooler than the west. El Nino attacks that system directly. When Kelvin waves surge eastward through the subsurface, they act like a giant hand pushing down on the thermocline. They force the cold, dense water deeper. In some parts of the eastern Pacific during a strong El Nino event, the thermocline gets pushed so deep that the cold water can no longer reach the surface at all. When that happens, warm water takes complete control of the surface. Temperatures rise fast. The atmosphere above responds within weeks. Scientists tracking the thermocline depth in early 2026 found something striking. The Kelvin waves moving through the Pacific had already pushed the thermocline significantly deeper than normal across large stretches of the central and eastern basin. The cold water that normally keeps the eastern Pacific cool was being forced out of reach. The ocean surface above those regions started warming faster. Here is why this matters beyond the science. When the thermocline drops deep in the eastern Pacific, the cold water upwelling that feeds one of the richest marine ecosystems on Earth slows down. Anchovies, sardines, and the massive food webs they support depend on cold, nutrient-rich water coming up from below. During the 1997 to 1998 El Nino, fish populations in the eastern Pacific collapsed. Seabird colonies failed. Sea lions starved. The ocean ecology and the global food chain are connected in ways that ripple all the way to grocery stores. And the thermocline is the hinge point. Once it gets pushed deep enough, the process becomes self-reinforcing. Warm surface water suppresses the upwelling further. The atmosphere above keeps feeding energy back into the ocean. The event grows stronger. In 2026, climate scientists confirmed the thermocline had already been pushed to depths comparable to what they saw in the early stages of the 2015 to 2016 event. The record holder, the benchmark everyone compares against. But 2015 had one thing 2026 may not. Time to build slowly. This event is moving faster, and what one leading scientist said publicly about its potential strength became one of the most quoted climate warnings of the year. Some forecasts get attention. This one stopped people cold. In May 2026, the European Centre for Medium-Range Weather Forecasts, one of the most respected climate modelling agencies in the world, released its long-range outlook for the coming months. The agency runs what many meteorologists consider the gold standard of global atmospheric modelling. Its forecasts are used by governments, militaries, and disaster agencies worldwide. The number it put on a super El Nino forming by November 2026 was 100%. Not 90, not 95, 100. That is essentially unheard of in seasonal climate forecasting. Forecasters deal in probabilities because the atmosphere is chaotic and complex. Saying something is 100% certain is something most scientists refuse to do, even when the evidence is overwhelming. The European model went there anyway. Buried in the details of that forecast was an even more striking projection. The model suggested that Central Pacific sea surface temperatures could warm by 3 degrees above average by late 2026. For context, the strongest El Nino in the modern record, the 2015 to 2016 event, reached about 2.5 degrees above average at its peak. 3 degrees would be beyond anything reliably measured in the modern era. To find a comparable event, scientists would have to go back to 1877. That year, an El Nino struck that killed an estimated 50 million people across Asia, South America, and Africa through drought, famine, and disease. Records from that era are incomplete, but climate historians working from proxy data like tree rings, coral samples, and historical harvest records have reconstructed the event as catastrophically powerful. The European model was not predicting a repeat of 1877, but it was flagging that the physical setup of the Pacific in 2026 had reached a level of intensity that puts the current event in conversation with that history. Scientists outside the agency were quick to add context. The European model is one data point. Other major forecasters, including NOAA and Australia's Bureau of Meteorology, were placing the odds of a super-strength event much lower, in the range of 23 to 37%. Scientists emphasised that the spring predictability barrier, which clouds all El Nino forecasts made before June, still introduced real uncertainty into any projection. A team of climate researchers summed it up this way: the subsurface signals in early 2026 were the most alarming they had seen since before the 2015 event. That does not guarantee a record, but it means the ceiling for how bad this could get is very high. The European forecast drew criticism from some quarters for overstate uncertainty, but it also drew something else: attention. Governments that had been watching the situation passively started asking harder questions. Emergency planners who had penciled in a moderate event started preparing for a severe one. One scientist stood at the centre of this debate. His warning carried unusual weight, because his specialty is exactly this kind of extreme El Nino formation. And what he said publicly in May 2026 is where the story gets personal. 1877. The telegraph existed. The steam engine was running. But climate science as we know it was decades away. Nobody understood what was happening to the global weather system. They just experienced it. What happened that year across Asia, Africa, and South America falls into a category of human suffering that is hard to fully grasp. The monsoon across India collapsed. For 2 consecutive years, rainfall failed across a vast stretch of South and East Asia. Crops withered. Rivers ran low. Grain stores emptied. Historians and climate scientists working from colonial records, ship logs, missionary accounts, and agricultural data have reconstructed the scale. An estimated 50 million people died. Some researchers put the number higher. The deaths came from starvation, disease, and the cascading collapses that follow when food systems break down across an entire continent. And it all traces back to one thing: an El Nino event so powerful that the climate system globally locked into an extreme pattern and stayed there for 2 consecutive years. Climate scientists today have reconstructed the 1877 event using proxy records. Coral samples from reefs in the tropical Pacific show chemical signatures that shift in response to temperature changes in the surrounding water. Tree rings from drought-sensitive forests in Asia and South America narrow and sometimes vanish during years of severe heat and dryness. These proxies give scientists a temperature fingerprint for what happened in 1877. The reconstruction suggests sea surface temperatures in the central Pacific during that event rose by roughly 3 degrees above the long-term average. That is the same number the European model projected for 2026. Scientists are careful about this comparison. The 1877 data is reconstructed, not directly measured. Modern infrastructure, early warning systems, and global food trade networks mean a comparable climate event today would not automatically produce the same scale of famine. The world has changed. But the physics of the atmosphere have not. An El Nino of that magnitude would still collapse monsoon systems. It would still drive multi-year droughts across Southeast Asia and parts of Africa. It would still suppress the cold water upwelling that feeds critical fisheries. The mechanisms are the same. The population at risk today is far larger than in 1877. India now feeds over 1,400,000,000 people, many of them dependent on a monsoon system that El Nino directly disrupts. The Philippines, Indonesia, and other Pacific island nations have grown enormously in population. Their agriculture, their water supply, and their power generation all lean heavily on predictable seasonal rainfall. The 1877 event happened before anyone understood El Nino. People suffered without knowing why. In 2026, scientists understand exactly what is building. The question is whether that understanding will translate into action fast enough to matter. And to answer that, it helps to look at a more recent event, one that the world actually watched unfold in real time, one that left scars still visible today. The summer of 1997 felt wrong. Across the Philippines, the rains that normally arrive with the southwest monsoon came late and sparse. Reservoirs that usually filled from June through August sat low into September. Farmers in the Cagayan Valley planted on schedule and watched their crops slow and shrink. Power plants that ran on hydroelectric energy started rationing output. The same story was playing out across Indonesia, Malaysia, Thailand, and Vietnam. The whole region was drying out. Rivers that had run reliably for generations were running low. Forest fires broke out across Sumatra and Borneo. The smoke was so thick that in some cities people wore masks just to go outside, and that was just Asia. In the southern United States, record rainfall battered California, Texas, and the Gulf Coast. Mudslides tore through hillsides that had been weakened by drought the previous year. Flooding caused billions of dollars in damage across multiple states. In East Africa, unusually heavy rains triggered floods that killed hundreds of people and displaced tens of thousands. The global death toll from the 1997 to 1998 El Nino is estimated at around 23,000 people. Economic losses ran into the tens of billions of dollars. Agricultural shortfalls drove food prices higher across Asia, hitting the poorest communities hardest. That event changed how the world understood El Nino. Before 1997, El Nino was something scientists tracked but the public barely noticed. Afterward, it became a household term. Governments started building monitoring networks. Forecasting agencies expanded their El Nino research programs. The Philippines and Indonesia created dedicated seasonal climate offices specifically to translate El Nino forecasts into farm-level guidance. The 1997 to 1998 event also revealed something important about how El Nino develops. It built fast. By mid-1997, sea surface temperatures in the central Pacific were already running well above normal. By the fall, the event had locked into a powerful state and stayed there through the spring of 1998. Scientists studying it afterward noticed a pattern. The subsurface ocean had been showing unusual heat months before the surface warmed. Kelvin waves had moved through the Pacific earlier that year. Trade winds had weakened. All the precursor signals were there for anyone tracking them. In 2026, forecasters are tracking those same signals, and they are showing up earlier and at greater intensity than they did in 1997. The 1997 event peaked at roughly 2 degrees above the long-term Pacific average, severe by any measure. And it caused what the world saw. The question now is what a significantly stronger event would look like. For that answer, scientists point to a more recent data point. The last time the world thought it had seen the worst El Nino possible. By mid-2015, forecasters knew something exceptional was coming. The Pacific was running hotter than it had in decades. Sea surface temperatures in the central equatorial Pacific climbed steadily through the year, reaching 2.5 degrees above the long-term average by the fall. Scientists at NOAA gave it the informal name the Godzilla El Nino because of how large and powerful it appeared on their monitoring systems. They were right to give it that name. Across the Philippines, the 2015 to 2016 event brought severe drought to agricultural regions that had already dealt with back-to-back dry spells. Crop yields fell, water rationing went into effect in multiple provinces. Electricity shortages hit communities dependent on reservoirs for hydroelectric power. The government declared a state of calamity in dozens of provinces. Indonesia and Malaysia experienced some of the worst droughts in decades. The fires that burned across Borneo and Sumatra in 2015 released carbon emissions comparable to what Germany produces in an entire year. Air quality across Southeast Asia collapsed for months. India recorded its second consecutive below-average monsoon. Reservoir levels fell to critical lows in several states. Farmers in Maharashtra and other drought-prone regions suffered back-to-back crop failures. In East Africa, a different problem emerged. El Nino brought excess rainfall to countries along the Horn of Africa and caused flooding that displaced millions. The same event that dried out Asia flooded parts of Africa. Globally, 2015 and 2016 both set new records for the hottest year in measured history. Scientists confirmed that El Nino's additional warming boost, layered on top of long-term climate warming, pushed both years past every previous benchmark. The total economic damage from the 2015 to 2016 event ran into the hundreds of billions of dollars worldwide when agricultural losses, infrastructure damage, and health costs were added together. And that event peaked at 2.5 degrees above normal. The European model's May 2026 projection places 2026's potential peak at 3 degrees. NOAA puts the odds of a very strong event at about 23%. The National Weather Service puts the odds of a super-strength event at 37% by November 2026. Paul Roundy, an atmospheric scientist at the University at Albany, who has spent his career studying El Nino formation, reviewed the 2026 data in May and stated publicly that there was real potential for the strongest El Nino event in 140 years. 140 years. That is 1877. Scientists cautioned that uncertainty remains high and that the spring predictability barrier means forecasts will sharpen significantly once June and July arrive. But the physical signals in the Pacific, the Kelvin waves, the subsurface heat, the weakening trade winds, the deepening thermocline, are running at levels that scientists rarely see at this point in an El Nino cycle. And these super-strength events are historically rare. Only 5 have been documented in the last 70 years. What makes that rarity so striking and so important is not just how few of them there have been, it is how differently each one formed, and why this year looks unlike any of them. 5. In the last 70 years of reliable ocean temperature records, scientists have counted only 5 El Nino events strong enough to be classified as super-strength. 1972 to 73, 1982 to 83, 1991 to 92, 1997 to 98, and 2015 to 2016. 5 events in 7 decades. That is roughly 1 every 14 years, but they do not come on schedule. The gaps between them range from a few years to over a decade, and their strength varies significantly even within that category. Some peaked at 2 degrees above normal, others pushed past 2.5. The rarity matters. It means each event is somewhat unique. Scientists cannot build a statistical rulebook for super El Ninos the way they can for moderate events, because there are so few data points to work from. Every time a potentially extreme event forms, researchers are partly working in territory they have limited precedent for. Here is what all 5 events had in common. Each one started with an unusually large reservoir of warm water in the subsurface Pacific. Each involved multiple Kelvin waves moving through the basin. Each saw a significant weakening of the trade winds, followed by a strong atmospheric response to the warming ocean. And each produced global disruptions that lasted well beyond the event itself. The aftermath tends to outlast the event. After the 1997 to 1998 event ended, La Niña followed. La Niña reversed the conditions, flooding regions that had just experienced drought and drying out regions that had just flooded. The swing from one extreme to the other sometimes caused more damage than either event alone. After 2015 to 2016, the global temperature records that had been set kept standing for years. The heat that El Nino added to the climate system did not fully dissipate. Scientists confirm that super events leave a thermal footprint that lingers in the ocean for years afterward. In 2026, the Pacific is showing multiple signals that match the early stages of those historical extremes, but there is one complicating factor that did not exist in 1972, or 1982, or even 1997. The baseline temperature of the ocean is higher now. Each of those 5 super events formed in a Pacific that was already warming due to long-term climate change, but the rate of that background warming has accelerated. The ocean that El Nino is forming in today is measurably warmer than the ocean that produced those historical events. The warm water reservoir has a higher starting point. The atmospheric system it is interacting with is more energized. Scientists studying this intersection confirm that climate change does not simply add a fixed amount of warming to El Nino. The relationship is more complex. A hotter background ocean means El Nino has more energy to draw from, which could allow events to intensify faster and peak higher than historical patterns would suggest. That is one reason the European model's 100% projection triggered such debate. And it is why one fundamental limitation in El Nino forecasting was suddenly getting discussed far outside the usual scientific circles. The calendar itself creates a problem, and for a few months every year, even the best forecasters in the world go partially blind. Every year, between March and May, something strange happens to El Nino forecasting. The models lose skill, confidence intervals widen, forecasts that would normally be reliable become genuinely uncertain. Scientists call this the spring predictability barrier, and it is one of the most frustrating, well-documented limitations in all of climate science. Here is why it happens. El Nino lives in the tropical Pacific, but the atmosphere above the tropics during boreal spring, meaning the northern hemisphere spring from March through May, is in a state of natural flux. The seasons are changing. Pressure systems that were stable through winter are shifting. The coupling between the ocean and the atmosphere, which is what El Nino relies on to sustain itself, is weaker and noisier during this transitional period. When the coupling is weaker, small errors in the model's starting conditions can grow quickly. A slight overestimate or underestimate of trade wind strength in March can cascade into a very wrong forecast by October. The atmosphere during spring is chaotic enough that even tiny differences in initial inputs lead to very different outcomes. The result is that forecasts issued between March and May for the following autumn and winter carry much higher uncertainty than forecasts issued in June or July. This matters enormously for 2026. Every major forecast released in the spring of 2026, including NOAA's 82% probability, the European model's 100% projection, and the various agency outlooks pointing toward a strong or very strong event, was issued during or just after the spring predictability barrier. The models were working with high uncertainty, even as they pointed in a consistent direction. Andrew Kruszkiewicz, a scientist at the Columbia University Climate Center, explained it plainly. Once forecasters reach June and especially July, the spring predictability barrier ends. Confidence rises sharply. The forecasts issued after that period are significantly more reliable for predicting what El Nino will do through the fall and winter. The 2026 World Meteorological Organization Bulletin from February is a clear example of how badly the barrier can distort early season forecasts. In February, the agency put only a 10% probability on El Nino developing by spring. By May, that number had been completely overtaken by events. The spring barrier works both ways. It can make an event look less likely than it is, or more likely. This is why NOAA, the Bureau of Meteorology in Australia, and the World Meteorological Organization all repeatedly stressed in their May 2026 communications that their projections would sharpen considerably once the Northern Hemisphere summer arrived. The World Meteorological Organization announced it would release a full El Nino update in late May 2026, timed specifically to catch the end of the spring barrier window. That update was expected to provide much cleaner guidance on peak strength and timing. For scientists already looking past the barrier, the underlying signals were hard to dismiss, but the public debate was increasingly being shaped by the most extreme projection in the room, and the scientist who put his name and reputation behind a warning, unlike anything issued in recent memory. Paul Roundy studies how El Nino forms. Specifically, he studies the atmospheric side. The way the winds respond to a warming ocean, the way pressure patterns shift across the tropics, the feedback loops that turn a moderately warm Pacific into something that reshapes global weather. He is based at the University at Albany and has spent years publishing research on tropical atmospheric dynamics. He is not a scientist who reaches for dramatic language. His work is technical, precise, grounded in data. In May 2026, he said something that got repeated in climate briefings around the world. He stated that the 2026 El Nino had real potential to become the strongest event in 140 years. 140 years puts the comparison in 1886, the era of the previous statement, the 1877 event, the one that killed tens of millions. Roundy's language was careful. He said potential. He acknowledged uncertainty. He pointed to the spring predictability barrier as a reason to keep updating the assessment as new data arrived. But the underlying point was clear. The physical setup of the Pacific in spring 2026 was in a class of its own compared to the last several decades. The Kelvin waves, the subsurface heat, the rate of atmospheric response, all of it was tracking at levels he had not seen in combination before. He cited two specific signals as his main concern. First, the unusually large reservoir of warm water sitting in the subsurface Pacific. Scientists measure this as heat content, and in early 2026 it was at one of the highest levels on record for this stage of an El Nino development cycle. That reservoir was the fuel. And there was more of it than in any recent comparable event. Second, the speed of development. El Nino events that develop faster than expected tend to peak higher than slower developing events. The acceleration seen between February and May 2026 was not just surprising to modelers. It suggested the system had more internal momentum than a typical forming event. Roundy stopped short of calling the event a certainty to break records. Science does not work on certainties. But his assessment placed 2026 in a different category from anything seen since the modern era of ocean monitoring began in the 1950s. Other scientists responded with varying degrees of agreement. Some said the European model's 100% projection was likely an overstatement of certainty. Others said NOAA's more conservative range was the right framing given the spring barrier. A few noted that even if the event peaked at moderate strength, the baseline warming from long-term climate change would amplify its real-world impacts beyond what the historical record would suggest. The debate was serious. The uncertainty was real. But behind all of it, in the data, the signals pointed in one direction. A strong El Nino was forming. How strong was still the question. And for the people living in the regions most directly in its path, that question was no longer abstract. It was landing on their farms, their water supplies, and their daily lives right now, starting with one of the countries sitting directly in El Nino's crosshairs. The Philippines has been through this before. Every strong El Nino puts this archipelago, spread across 7,000 islands in the Western Pacific, directly in its path. El Nino reliably brings drier than normal conditions to the Philippines, less rainfall, lower reservoir levels, reduced river flow, agricultural stress across the major grain-growing regions. The country has been through enough El Niños to know the pattern. But knowing the pattern and being ready for it are not the same thing. On April 22, 2026, PEGASA issued a formal El Nino alert. This is an official signal that conditions have shifted enough to warrant action. The alert went to local government units, the agricultural department, the energy sector, and the National Disaster Reduction Agency. It triggered a chain of protocols that planners had worked out after the 2015 to 2016 event. But the timeline was compressed. The alert came almost 2 months earlier than the forecasting community had expected to issue it. The rapid development of the Pacific warming means that the window for preparation, planting schedule adjustments, water conservation measures, and emergency food stockpiling had shrunk considerably. Farmers in Luzon and the Visayas plant their main rice crop based on seasonal rainfall patterns. A strong El Nino changes those patterns significantly. Rainfall during the growing season can drop 30 to 40% below normal in some regions. Without irrigation infrastructure to compensate, that means crop stress, reduced yields, and in severe cases total crop failure in affected areas. Rice is not the only concern. Corn production in Mindanao, sugarcane in Negros, and vegetables grown across highland regions are all sensitive to rainfall. A multi-month dry spell during the 2015 to 2016 event led to significant food price increases in local markets and required emergency government intervention. The energy sector faces a related problem. Around 20% of the Philippines' electricity comes from hydroelectric sources. When reservoir levels drop during extended dry spells, hydroelectric output falls. The shortfall has to be covered by fuel-burning plants, which are more expensive and increase power costs for households and businesses. During the 2015 to 2016 El Nino, some provinces experienced rotating brownouts for weeks as reservoir-fed plants ran below capacity. PEGASA's April 2026 forecast placed a 79% probability on El Nino being active through the June through August season, with a likely continuation into early 2027. That duration matters. A brief El Nino might cause one dry season. An event that persists through early 2027 would hit 2 consecutive growing seasons. Scientists at PEGASA and international agencies working with the Philippines government confirmed the projections and began coordinating with agricultural planners on adaptive strategies. The Philippines is experienced at responding to El Nino. The country has systems, early warning networks, and institutional memory built from previous events. But those systems were designed around El Niños of a certain strength and timing. What is forming in 2026 may exceed the parameters those systems were built for, and the Philippines is far from alone. To the northwest, across the Bay of Bengal, more than 1 billion people were watching a different set of weather signals with growing concern. 600 million farmers, that is roughly how many people in India depend directly on the monsoon for their livelihoods. The monsoon is the seasonal shift of winds that drives enormous amounts of moisture-laden air from the Indian Ocean onto the subcontinent between June and September. It delivers roughly 80% of India's annual rainfall in that 4-month window. When it works, it feeds a nation of 1,400,000,000 people. When it weakens, the consequences move fast. India's meteorological department issued a cautious forecast for the 2026 monsoon season in May. Officials stated the monsoon rainfall could fall below the long-term average. If confirmed, it would be the first below-average monsoon in 3 years. The timing, arriving in the same season as a developing El Nino, was consistent with a well-documented historical pattern. Scientists confirmed decades ago that El Nino and the Indian monsoon are connected. The mechanism runs through the Walker circulation, a planet-scale loop of rising and sinking air driven by temperature differences across the tropical Pacific and Indian Oceans. When El Nino warms the central Pacific abnormally, it disrupts this circulation. The atmospheric rising motion that normally sits over the Indian Ocean and helps pull the monsoon onto the subcontinent weakens. The moisture flow slows. The effect is not always dramatic during a moderate event, but during strong and very strong El Niños, the monsoon shortfall can be significant. During the 2015 to 2016 event, India recorded 2 consecutive below-average monsoon seasons. Maharashtra, Uttar Pradesh, and Madhya Pradesh experienced severe agricultural stress. Farmers in multiple states faced crop failures. The Indian government deployed emergency food programs and drought relief across hundreds of districts. A similar scenario in 2026 would arrive in a context of already elevated food prices and energy costs globally. The compounding effect matters. El Nino does not just hit one country at a time, it hits multiple regions simultaneously, which means the global food system faces stress from multiple directions at once. India's wheat and rice output are among the most consequential agricultural variables on the planet. India is one of the world's largest grain producers and a critical buffer when other regions face shortfalls. If the 2026 monsoon runs significantly below average, India's exportable surplus shrinks. Countries that rely on Indian grain supplies across Africa and parts of Southeast Asia feel that squeeze directly. Scientists studying the 2026 signals emphasize that the monsoon forecast carries its own uncertainty, separate from the El Nino strength question. The monsoon has shown some resilience to El Nino's influence in recent years, partly because the Indian Ocean itself has warmed, creating a partial counterweight to Pacific-driven disruption. But that counterweight has limits. Strong El Niños have historically overwhelmed it. The India Meteorological Department was scheduled to release an updated monsoon forecast after the spring predictability barrier passed. Agricultural planners across multiple states were already working from contingency scenarios that assumed a below-normal season. The stakes are enormous, and for a country with this many people depending on this single seasonal weather pattern, the margin for error is extremely thin. What happens to India's farmers in 2026 will ripple through global food markets, government budgets, and the daily lives of people who have never heard the words El Nino in their lives. Australia has a saying that weather forecasters use internally. When El Nino forms, call Eastern Australia first. The eastern side of the continent, where most of the population lives and where most of the grain, cotton, and beef production happens, sits directly in the path of El Niño's drying effect. When the Pacific warms abnormally, the rainfall that normally builds over the warm western Pacific and eventually reaches eastern Australia weakens. The moisture source shifts. The rain stops arriving. Australia's Bureau of Meteorology was tracking the 2026 Pacific signals closely from early in the year. By May, it had shifted its seasonal rainfall outlook for eastern cropping regions to below average from May through August. That window covers the tail end of the southern hemisphere autumn and the beginning of winter, a critical period for planting wheat and other winter cereals across New South Wales and Victoria. Wheat is not just an Australian food staple. Australia is one of the world's major wheat exporters. Its crop output matters to bread prices in Indonesia, the Philippines, Egypt, and dozens of other countries that import Australian grain. The 2019 to 2020 Australian drought, driven partly by a moderate El Nino pattern, was one of the most severe in the country's recorded history. Crop output fell dramatically. Cattle herds were culled as pasture dried up. Bushfires tore through eastern Australia on a scale that shocked even veteran firefighters. The fires burned through an area roughly the size of the entire state of Virginia. That event happened during a moderate El Nino. Scientists confirmed it. In 2026, the Bureau of Meteorology was placing about 50% odds on El Nino developing to meaningful strength by late in the year. That number was lower than NOAA's or the European model's estimates, reflecting genuine uncertainty among agencies about peak intensity. But even at moderate strength, the Bureau's seasonal models showed meaningful drying across the Murray-Darling Basin. the agricultural heartland of southeastern Australia. The Murray-Darling Basin produces about 40% of Australia's agricultural output. It grows rice, cotton, grapes, citrus, and the majority of the country's vegetable crop. It is also where most of Australia's irrigation water comes from. Reduced rainfall into the basin means lower river flows, declining reservoir levels, and reduced allocations to farms. Farmers in the basin were already working from the assumption that 2026 would be a dry year. Planting decisions made in April and May reflected that. Some scaled back water-intensive crops, others held off on expansion plans that required reliable irrigation access. The Bureau of Meteorology was updating its outlook monthly and communicating directly with state agricultural departments. Unlike the 2019 drought, which caught some planning agencies underprepared, the 2026 event had the advantage of an early warning signal. Whether that early warning translated into effective preparation depended on how quickly local governments and farm communities could act. And Australia was facing one more factor that did not exist in 2019 in the same way. The ocean surrounding the continent was warmer than it had been during any previous El Nino. Warmer surrounding seas mean faster evaporation, more intense heat events, and potentially more extreme fire conditions when the dry season arrived. Eastern Australia was preparing. But what was coming toward the Atlantic Ocean from the opposite direction was something El Nino almost always flips into an advantage for one specific group: hurricane forecasters. Every August, the Atlantic hurricane season enters its peak. Storms build over the warm tropical Atlantic, organize into spiraling systems, and move toward the Caribbean, the Gulf of Mexico, and the coastlines of the southeastern United States. On average, the Atlantic produces about 14 named storms per season and 7 hurricanes. Some years are quiet, some are catastrophic. El Nino changes the math. Here is the mechanism. Strong El Niños pump extra energy into the atmosphere over the tropical Pacific. That energy drives faster, stronger winds at high altitude across the Pacific and crucially across the Atlantic. These high-altitude winds blow parallel to the ocean surface, but in a direction that cuts across developing tropical storms. Scientists call this wind shear, and wind shear is one of a hurricane's worst enemies. A tropical storm needs a calm, organised atmosphere to develop. It spins up by pulling warm, moist air from the ocean surface, rising rapidly through the atmosphere and releasing that heat high above. If strong high-altitude winds are blowing sideways across the storm structure, they tear it apart. The organised circulation breaks down. The storm weakens or fails to develop at all. During strong El Nino years, Atlantic hurricane counts drop measurably. Scientists confirmed this relationship after studying decades of storm records alongside Pacific temperature data. For the 2026 season, the European Centre for Medium-Range Weather Forecasts was forecasting 13 named storms and 6 hurricanes in the Atlantic. Both numbers fall just below the long-term average. For people living along the Gulf Coast or in the Caribbean, that is moderately good news. But the same atmospheric shift that suppresses Atlantic storms does the opposite in the Pacific. El Nino reduces wind shear over the central and eastern Pacific, creating conditions that favour stronger and more frequent Pacific hurricanes and typhoons. For the Philippines, Japan, Taiwan, and other Western Pacific nations, this is significant. The Western Pacific typhoon season can be intense even in neutral years. During strong El Nino events, the tracks and intensities of typhoons can shift in ways that bring more severe storms to regions not accustomed to direct hits. Scientists monitoring the 2026 Pacific typhoon season were already flagging elevated risk for the Western Pacific Basin. There was another wrinkle to the Atlantic story. Even with suppressed overall activity, El Nino does not prevent individual major hurricanes. It reduces the total count but does not guarantee a quiet season for any specific coastline. The 1997 to 1998 El Nino suppressed Atlantic storm counts overall. It still produced Hurricane Mitch, which killed nearly 11,000 people in Central America and remains one of the deadliest Atlantic hurricanes on record. NOAA's Seasonal Hurricane Outlook, released in May 2026, reflected this nuance. The agency called for a below-average season, but explicitly warned that even one landfalling major hurricane can cause catastrophic damage regardless of total seasonal activity. For emergency managers along the Gulf Coast, El Nino offered partial relief. Reduced storm counts lowered overall risk, but they continued to prepare for the possibility that the one storm that did develop would be severe. And while forecasters focused on the Atlantic, the same El Nino was quietly rearranging the rainfall map of the continental United States in ways that the Southwest and South were already starting to feel. California has a complicated relationship with El Nino. During strong events, the state can shift from severe drought to heavy rainfall and catastrophic flooding within a single season. The jetstream, the river of fast-moving air that steers storms across North America, bends southward during El Nino. It pushes storm tracks into the southwestern United States, particularly California, Arizona, and New Mexico, regions that spend most years receiving very little winter rain. The results are dramatic. During the 1997 to 1998 El Nino, California received rainfall totals far above normal across most of the state. Flooding damaged roads and communities across the Central Valley. Mudslides tore through hillsides that had been stripped bare by drought in previous years. Reservoirs that had been dangerously low filled rapidly, but the infrastructure handling the inflow, spillways, channels, and levees was not always built for that volume of water arriving that fast. The 2015 to 2016 El Nino raised expectations of a similar soaking for California. Scientists predicted above normal rainfall. Some forecasters used the phrase the miracle march to describe the expected late-season rain. The results were more complicated. Southern California received above-average precipitation. Northern California received less than predicted. The event was real but uneven in its distribution. That variability is one of the most important things to understand about El Niño's effects on any specific region. The large-scale pattern is consistent. The local details are not. Forecasters can say with confidence that El Nino tends to bring above normal precipitation to the southwestern United States. They cannot say with the same confidence exactly which valleys will flood or which hillsides will slide. For 2026, NOAA's seasonal outlook pointed toward above normal precipitation across the southern tier of the United States from California through Texas and across the Gulf Coast states. The southern jet stream pattern associated with strong El Nino events was expected to drive a wetter-than-average winter for those regions. At the same time, the Pacific Northwest and the northern Great Plains were expected to see below normal precipitation and above normal temperatures during the same period. El Nino does not simply make the United States wetter, it shifts the rainfall map, with some regions getting more and others getting less. For farmers in the southern plains, above normal winter precipitation could help recharge soil moisture going into spring planting. For northern wheat country, a dry and warm El Nino winter could stress winter wheat crops that need moisture to survive the cold months. The economic stakes for American agriculture are significant. The United States produces roughly 15% of global wheat exports and is a major producer of corn, soybeans, and cotton. Shifts in regional precipitation patterns during a strong El Nino translate directly into crop yield changes that move global commodity prices. And the commodity price effect of a strong El Nino does not stay in one country's agricultural sector, it spreads. Because when rainfall patterns shift across multiple continents simultaneously, the entire global food system feels the pressure at once. Picture a scale with the world's food supply on one side and the world's population on the other. Most years, the scale stays roughly balanced. Record harvests in one region offset shortfalls in another. Global grain reserves absorb moderate disruptions. Prices fluctuate, but within ranges that most economies can manage. El Nino breaks that balance. A A strong event does not hit one crop in one country. It hits multiple crops across multiple continents at the same time for the same underlying reason. The same atmospheric shift that dries out Southeast Asia also disrupts India's monsoon, stresses Australia's grain belt, and alters rainfall across parts of Africa. All of those regions produce food that feeds the rest of the world. Scientists studying the relationship between El Nino and food prices confirmed a consistent pattern. During strong events, global prices for rice, wheat, and vegetable oils tend to rise. The increases are not random. They follow directly from the geographic pattern of El Nino-driven crop losses. Rice is the most sensitive. The major rice-producing nations, Thailand, Vietnam, India, the Philippines, and Indonesia, all sit in the tropical Asia-Pacific zone that El Nino dries out most severely. When multiple countries in that group experience below normal monsoon rainfall in the same season, global rice supply drops and prices respond quickly. During the 2015 to 2016 event, vegetable oil prices spiked sharply. Indonesia and Malaysia together produce about 85% of the world's palm oil. Both countries experienced severe drought during that event, reducing palm fruit yields. Palm oil is used in food products, cosmetics, and biofuels worldwide. When its price rises, it pulls other vegetable oil prices up with it and raises production costs across the global food industry. Wheat is the third pressure point. Australia and India are major wheat exporters. El Nino dries out Australia's eastern wheat belt and weakens India's monsoon, which affects winter wheat in northern India. When both suppliers face shortfalls in the same year, the global wheat market tightens. The compounding effect matters most for low-income countries. Nations that spend a high share of household income on food across sub-Saharan Africa, South Asia, and parts of Southeast Asia feel food price spikes immediately and severely. International food agencies tracking the 2026 El Nino development were already flagging elevated risk for food insecurity across those regions. The World Food Programme confirmed in its May 2026 regional assessments that populations in the Horn of Africa, parts of Southern Africa, and vulnerable communities across Southeast Asia faced heightened risk if the El Nino event developed at the strong end of the projected range. For wealthier countries, the food price impact is real but manageable. Grocery bills rise. Certain products become more expensive. For the world's poorest communities, the same price movement can tip a family from food security into hunger. El Nino does not cause famine by itself. The 2026 event will not create the kind of catastrophe that 1877 did. But in regions already dealing with poverty, conflict, or climate stress, a food price spike triggered by a strong El Nino can push fragile situations past a breaking point. And layered on top of all of this food system pressure is a warming that goes beyond any single season. Every year for the past decade has competed for the same title, hottest year on record. The record has moved so frequently that climate scientists now treat new temperature benchmarks as near certain before the year even ends. 2023 set a record. 2024 broke it. The long-term warming trend driving these records is separate from El Nino. It runs in the background constantly, driven by the accumulation of greenhouse gases in the atmosphere. But El Nino adds a boost, and in years when a strong El Nino peaks, the boost can push global average temperatures well above what the background trend alone would produce. NOAA stated in May 2026 that it was very likely 2026 would rank among the 5 hottest years ever recorded, even accounting for uncertainty. That assessment was made before the full strength of the developing El Nino was known. Here is why the two signals stack. The background warming trend has been raising global average temperatures by roughly 0.2 of a degree per decade for the past several decades. That is a steady, relentless climb. El Nino adds a temporary spike on top of it. During strong events, the spike can add 2 to 0.3 of a degree above the already elevated baseline to the global annual average. 2.5 degrees of Central Pacific warming during a super El Nino produces a global temperature fingerprint. The warm ocean heats the air above it. The atmosphere circulates that warmth globally. Every continent sees temperatures nudged upward, even regions far from the Pacific. Scientists studying the 2015 to 2016 event confirmed that both 2015 and 2016 set new records for global average temperature precisely because the El Nino boost was stacked on top of long-term warming. The 1-2 combination pushed both years past every previous benchmark. If 2026 event develops at the strength the European model projected, or even at the lower end of NOAA's strong event range, the temperature implications are significant. A super El Nino peaking in late 2026 would add its maximum warming boost to the global average in 2027, as the ocean heat takes several months to fully express itself in atmospheric temperature records. Scientists studying this timeline noted that 2027 could actually set a larger temperature record than 2026, depending on when the event peaks. For the public, these temperature records carry consequences beyond scientific benchmarks. Record heat drives more intense heat waves across multiple continents simultaneously. Heat waves kill people directly. They stress agricultural systems. They increase wildfire risk. They push power grids to failure. But behind the temperature record question is something deeper. Something that makes 2026's El Nino fundamentally different from every event that came before it. The ocean it is forming in is warmer than it has ever been at the start of an El Nino cycle, and that background warming is not separate from the event. It is now part of the fuel. For most of El Nino's recorded history, climate change and El Nino were treated as two separate conversations. El Nino was a natural cycle. Climate change was a long-term human-driven trend. Scientists studied them separately. Forecasters modelled them separately. Policy discussions treated them as different problems. That separation is no longer accurate. The ocean that El Nino forms in today is measurably warmer than the ocean that produced the 1982 to 1983 event, or the 1997 to 1998 event. The global average ocean surface temperature has risen by roughly 1 degree over the past century. That may sound small, but for an event that draws its power from the temperature contrast between the equatorial Pacific and the rest of the ocean system, a warmer baseline changes the math. Here is the key interaction. El Nino adds anomalous warming on top of whatever the baseline already is. When the baseline was cooler, an El Nino warming of 2.5 degrees above normal pushed the Pacific to a certain absolute temperature. When the baseline is a full degree warmer, the same 2.5 degrees of El Nino anomaly pushes the absolute temperature higher still. The atmosphere responds to absolute temperature, not just the anomaly. More heat at the surface means more energy available to drive atmospheric disruption. Scientists studying the most recent decades of El Nino events confirmed that strong events are producing more extreme impacts per unit of Pacific warming than they did in previous generations. The same strength event causes more damage today than it would have 50 years ago because the background system is already closer to its limits. There is a second interaction that climate researchers flag specifically for 2026. The deep ocean has been absorbing heat from the warming atmosphere for decades. That absorbed heat sits in the subsurface, adding to the reservoir that Kelvin waves draw on and that the thermocline locks away from the surface. In other words, the fuel supply for El Nino is larger than it used to be. Scientists are careful not to state that climate change is making El Nino events more frequent. The historical record does not clearly show that. What the evidence does show is that when El Nino events occur, they have more energy available to them than they did in previous eras. Extreme events are more likely to reach the upper end of the intensity scale. The 2026 event is the first potential super El Nino to form in an ocean that has spent 2 full additional decades absorbing greenhouse gas-driven warming compared to the 2015 to 2016 event. That additional decade of warming matters. It raises the ceiling on how intense this event could become. And it means the subsurface heat reservoir that has been building, the one Kelvin waves are pushing toward the surface right now, is likely the largest ever measured at the start of an El Nino formation cycle. And that reservoir is worth understanding directly. because the sheer scale of it is unlike anything scientists have measured in the modern era. Imagine filling a container the size of the continental United States with water heated to temperatures 6 to 7 degrees above normal. Now imagine that container is sitting 800 feet below the surface of the Pacific Ocean, invisible from above, slowly being pushed upward. That is roughly what scientists were measuring in the equatorial Pacific in early 2026. The technical term is ocean heat content. It measures how much thermal energy is stored in a column of water from the surface down to a specific depth, usually around 700 meters, which is just under half a mile. Scientists track this number across the entire Pacific basin using a network of deep-diving robotic sensors called Argo floats. Roughly 4,000 of these devices drift through the world's oceans, descending and rising on programmed cycles, transmitting temperature and salinity data to satellites above. The Argo network confirmed what the Kelvin wave tracking had suggested. In early 2026, the subsurface heat content of the equatorial Pacific was at one of the highest levels recorded in the history of the program. This is the reservoir Paul Roundy cited as one of his two primary reasons for concern. The size of the heat store determines the upper limit of what an El Nino event can do. A large reservoir means the event has sustained fuel. Even if surface conditions fluctuate month to month, the heat sitting below can keep feeding the system. During the 2015 to 2016 event, the subsurface heat content peaked at record levels for that era. Scientists studying the build-up afterward noted that the reservoir was the critical factor in allowing the event to sustain its intensity through 3 full seasons rather than weakening after 1 or 2. In 2026, the reservoir reached comparable levels months earlier in the development cycle. That timing matters. A large reservoir early in the cycle gives the event more time to draw on that fuel before the natural dissipation processes that eventually end every El Nino begin to take effect. The longer a strong El Nino sustains itself, the more cumulative damage it causes through extended drought, prolonged disruption to monsoon timing, and sustained pressure on agricultural systems. Pegasa's April 2026 forecast included a projection that the event would persist into early 2027. If the subsurface reservoir sustains the event at strong intensity through the end of 2026, a multi-season impact for the Philippines, India, and Australia becomes increasingly likely. The reservoir also explains why the spring predictability barrier is particularly frustrating for 2026's forecast. The subsurface heat content is clearly enormous. That part of the picture is confirmed, but translating reservoir size into peak intensity requires modelling the full atmospheric response, which is exactly what the spring barrier makes unreliable. Scientists knew the fuel was there. They were still working out how efficiently the engine would burn it, and the spark that ignites that engine, the mechanism that converts stored subsurface heat into a full-scale surface event, is something that forecasters were watching very carefully in the Western Pacific. In the Western Pacific, near the equator, the trade winds normally blow from east to west. Steady, predictable, the same direction they have blown for as long as sailors have crossed this ocean. But occasionally, something disrupts that flow. For a few days or a few weeks, the winds near the equator in the Western Pacific reverse direction. They blow west to east instead of east to west. Scientists call these events westerly wind bursts. They are short-lived, they are intense, and during the build-up of an El Nino, they act like a match dropped into a room that has been slowly filling with gas. Here is what a westerly wind burst actually does. When winds suddenly blow eastward along the equator, they push warm surface water eastward rather than westward. That eastward push adds momentum to the Kelvin waves, already moving through the subsurface. It deepens the thermocline further in the eastern Pacific, and it delivers warm surface water directly to the central Pacific, where El Nino needs it most to sustain its growth. A single westerly wind burst does not make or break an El Nino, but a series of them, arriving over the course of weeks or months, can dramatically accelerate an event's development. In early 2026, westerly windbursts were appearing in the monitoring data with increasing frequency near the equatorial western Pacific. Paul Roundy cited this as one of the signals that gave him concern, not because any individual burst was unprecedented, but because the sequence of them, combined with the pre-existing Kelvin waves and the massive subsurface heat reservoir, created a compounding effect. Each burst added energy to a system that was already running ahead of schedule. Scientists studying the 2015 to 2016 El Nino afterward identified westerly windbursts as a key contributor to that event's rapid intensification. Multiple bursts in the Western Pacific through 2014 and early 2015 accelerated the event's timeline and helped push it past the intensity levels that early models had projected. The 2026 sequence of bursts was showing up in data at a comparable stage of development to the 2015 timeline, but with a larger underlying heat reservoir to draw on. Forecasters watching this combination were treating it as a signal that the atmospheric response to the warming ocean, the part of the El Nino feedback loop that is hardest to predict and most critical to get right, was engaging earlier than expected. When the atmosphere locks into a feedback with the warming Pacific, the event enters a self-sustaining phase. The ocean heats the air above it, the altered air pressure changes the winds, the changed winds push more warm water into place, the cycle feeds itself. Breaking out of it requires the slow dissipation processes that only kick in months later, usually when the event's warm water supply depletes, or cold water begins to resurface in the east. In spring 2026, the feedback was beginning to engage. The models were updating their projections monthly as the atmospheric response became more visible in the data. And those updates were landing at the desks of forecasting agencies that were already disagreeing, sometimes significantly, about where this event was heading. 4 major agencies, 4 different answers. When scientists disagree on something as important as the strength of a potential record-breaking El Nino, the disagreement itself becomes part of the story. And in spring 2026, the gap between the most bullish and most conservative forecasters was wider than in any recent El Nino cycle. The European Centre for Medium-Range Weather Forecasts sat at one extreme. 100% probability, Super El Nino by November, Central Pacific temperatures potentially reaching 3 degrees above normal, the strongest event since 1877. NOAA sat at a more cautious position, 82% probability of El Nino forming by July, 66% chance of a strong or very strong peak, 23% odds of a super-strength event by October through December. Clear alarm, but significant uncertainty retained. The Japan Meteorological Agency put 70% odds on El Nino developing through the Northern Hemisphere summer, projecting a strong event without committing to a super-strength classification. Australia's Bureau of Meteorology was the most conservative of the major agencies, roughly 50% odds on a meaningful event, forecasting weak to moderate strength as the most likely outcome, noting the cooling of the cold tongue in the eastern Pacific as a signal worth watching, but maintaining that the spring barrier made strong confidence unwarranted. 4 agencies, probabilities ranging from 50 to 100%, projected peak strengths ranging from weak to moderate to the strongest in recorded history. This kind of spread is not a failure of science. It reflects the genuine uncertainty of predicting a chaotic system through the most difficult forecasting window of the year. Each agency uses different models, different weighting systems for ensemble runs, and different thresholds for how they translate raw model output into public probabilities. The European model is known for running warm compared to other global models in its long-range projections. Its El Nino forecasts have historically skewed towards stronger events. That does not mean it is wrong in 2026, but it is context worth noting. NOAA's ensemble approach deliberately averages across model runs to reduce overconfidence in any single outcome. Australia's Bureau of Meteorology focuses heavily on the local Pacific signals, most relevant to Southern Hemisphere impacts, which leads it to weight slightly different data streams than Northern Hemisphere-focused agencies. For decision makers in agriculture, emergency management and government planning, this spread of forecasts creates a difficult problem. Preparing for a super El Nino costs significantly more than preparing for a moderate one. If the conservative forecast is right and the extreme one is wrong, resources get spent on preparations that were not needed. If the conservative forecast is right and planners followed the extreme one, they are caught unprepared. Most agencies dealing with this in May 2026 were making the same calculation quietly. The cost of under-preparing for a super El Nino outweighs the cost of over-preparing for a moderate one. Better to mobilize resources for a worst-case scenario that does not fully materialize than to mobilize for a moderate scenario that turns out to be catastrophic. One part of the world would feel that calculation in a way that is impossible to measure in dollars or crop yields. Beneath the surface of the ocean, in warm, shallow waters across the tropical Pacific, something irreplaceable was already starting to die. Coral reefs cover less than 1% of the ocean floor. They shelter roughly 25% of all marine species on Earth. That imbalance between how little space they take up and how much life they support makes them the most productive ecosystems in the ocean, and they are among the most vulnerable things on the planet to El Nino. Here is the mechanism. Coral polyps, the tiny animals that build reef structures, live in a narrow temperature window. They thrive in water between about 70 and 85 degrees Fahrenheit. When water temperatures rise above that range, even briefly, corals respond in a predictable and devastating way. They expel the microscopic algae living inside their tissue. Those algae, called zooxanthellae, are what give coral its colour. They are also what provide the coral with up to 90% of its energy through photosynthesis. When the algae leave, the coral turns white. Scientists call this bleaching. The coral is still alive at that point, but it is running on nothing. If the heat stress lasts more than a few weeks, the coral starves and dies. El Nino pushes ocean surface temperatures in the tropical Pacific significantly above normal, across enormous stretches of reef systems. The Great Barrier Reef off northeastern Australia, the reefs of the Philippines and Indonesia, the coral systems across the central Pacific Islands, all of them sit in waters that El Nino heats directly. During the 2015 to 2016 El Nino, scientists documented the most extensive coral bleaching event ever recorded. An estimated 30% of the world's coral reefs experience bleaching. On the Great Barrier Reef, the northern section, which had been largely healthy going into the event, lost roughly half of its shallow water coral within 12 months. Scientists confirmed the cause directly, and the damage in many regions was permanent. Coral can recover from bleaching if temperatures drop quickly enough, but recovery takes years to decades. Reefs that bleached severely in 2016 were still in early stages of recovery in 2025. A second major bleaching event, arriving in 2026 before those systems fully recovered, could push some reef systems past a point of practical recovery within human timescales. The consequences extend beyond ecology. Coral reefs protect coastlines from wave damage. They provide food and income for hundreds of millions of people through fishing and tourism. In the Philippines alone, reef-dependent fishing supports over 1 million fishing households. The economic value of the Great Barrier Reef to Australia runs into billions of dollars annually through tourism. A super El Nino in 2026 would deliver another massive heat pulse to reef systems that are already weakened. Scientists monitoring sea surface temperatures across the Indo-Pacific in spring 2026 were already recording above normal temperatures in reef zones before El Nino had fully developed. When El Nino added its warming on top of already elevated baselines, the thermal stress on reefs would arrive faster and hit harder than in any previous event, and the ocean damage would not stay under the surface. Because what El Nino does to the air above those warm waters changes something fundamental about how storms move across entire continents. The jet stream is a river of air. It flows about 7 miles above the Earth's surface, moving from west to east at speeds that can exceed 200 miles per hour. You cannot see it. You cannot feel it directly. But it determines where storms go, how cold your winters are, and whether your region gets soaked or parched during any given season. El Nino bends it. When the tropical Pacific warms abnormally, it changes the temperature contrast between the tropics and the poles. That contrast is what drives the jet stream's position and strength. A warmer tropical Pacific pushes extra heat into the upper atmosphere, which shifts the jet stream's path in very specific, measurable ways. During strong El Nino events, the northern jet stream across the United States and Canada tends to shift northward over the Pacific and then dip sharply southward over the central United States. This creates a pattern where the Pacific Northwest and Canada receive warmer and drier conditions, while the southwestern and southern United States receive more storms and rainfall. That pattern also determines where cold Arctic air can break through into the continental United States. With the jet stream in an El Nino configuration, the barrier that normally blocks Arctic air from pushing too far south weakens over some regions and strengthens over others. In practical terms, this means cities that consider themselves outside typical flood zones can suddenly face extraordinary precipitation. During the 1997 to 1998 El Nino, parts of the Pacific coast received months of rainfall in a matter of weeks. Entire neighbourhoods built on hillsides that had been dry for years collapsed into mudslides. The jet stream shift also explains why El Nino and flooding are connected in places as far from the Pacific as the Eastern Mediterranean and the Horn of Africa. The atmospheric wave patterns triggered by Pacific warming travel around the globe, creating predictable pressure anomalies that shift rainfall dramatically across regions thousands of miles from the Pacific. Scientists confirmed these teleconnection patterns using decades of satellite data, weather station records, and advanced atmospheric modelling. The pathways are real and measurable. For 2026, forecasters modelling the jet stream response to a strong El Nino were projecting the familiar southern tier wetting pattern across the United States, combined with drying across Australia and enhanced dryness across Southeast Asia. The stronger the El Nino peaked, the more extreme these jet stream distortions would become. One of the most visible and destructive consequences of that drying, in a region already stressed by years of logging and land clearing, was something that could be seen from space, and the smoke had not even started rising yet. In September 2015, the sky over Singapore turned orange, not at sunset, in the middle of the afternoon. The haze came from Borneo and Sumatra, across the South China Sea, carried by winds from fires burning across hundreds of thousands of acres of peatland and forest. The fires had been burning for weeks. Some had been smouldering underground for months before finally breaking through the surface. Schools closed, airports reported reduced visibility, health advisories went out across 6 countries. The 2015 fires were directly tied to the El Nino drought that had dried out the region for months before the burning season began. Scientists confirmed the link. El Nino did not start the fires. People did, through land clearing and agricultural burning. But El Nino removed every natural defence the forest had against them. Soil moisture dropped to critical lows. Rivers that normally slow the spread of ground fires ran too shallow to act as barriers. The peat beneath the forest surface, which holds enormous amounts of water when hydrated, dried out and became fuel. Once peat ignites, it burns slowly and almost impossibly deep. Firefighters cannot reach underground combustion. It extinguishes only when rainfall returns in sufficient volume to saturate the soil again. The 2015 peat fires across Indonesia released an estimated 1.7 billion tons of carbon dioxide into the atmosphere over a few months. Scientists studying the event confirmed that figure exceeded Germany's total annual carbon emissions. The regional air quality collapse caused a measurable increase in respiratory illness across Southeast Asia, with the heaviest toll on children and elderly populations. El Nino in 2026 would deliver the same type of drought to those same forests, and the forests were entering this event more stressed than they were in 2015. Years of land clearing for palm oil plantations had reduced the natural buffer of intact forest. Ground moisture levels going into the dry season were already lower than historical averages due to the warming background climate. Australia faced a parallel risk. The 2019 to 2020 bushfire season, driven partly by El Nino-related drought, burned through an area approaching 30 million acres across eastern Australia. That event was so severe that smoke from the Australian fires crossed the Pacific Ocean and affected air quality in South America. Ecologists studying the recovery of those burned landscapes noted in 2026 that many of the most severely affected areas were still in early stages of ecological recovery. Forests that had not fully regrown their protective canopy were more vulnerable to fire in a second major drought event. An El Nino-driven drought in 2026 would not give those landscapes additional time to recover. It would arrive while the scars from the previous crisis were still fresh. And all of these risks, the reef bleaching, the drought, the fires, the monsoon failures, were converging toward a single moment in the calendar when the forecasting community expected to finally get a clear answer about what 2026's El Nino would actually do. Every month, the world's major climate agencies release updates. Most of those updates get read by meteorologists, agricultural planners, and government risk officers. They rarely make international news. The World Meteorological Organization's late May 2026 El Nino update was different. Scientists and climate policy officials across multiple continents were treating it as the most consequential seasonal climate forecast issued in at least a decade. The reason came down to timing. The update was scheduled to land just as the Northern Hemisphere passed through the end of the spring predictability barrier, the window of high uncertainty that had been clouding all El Nino forecasts since March. Once that barrier passed, the atmosphere-ocean coupling in the tropical Pacific becomes much more stable and readable. Models that had been running wide probability ranges through March, April, and May would suddenly tighten. The ensemble spread, meaning the range of possible outcomes different model runs produce would narrow. Forecasters would be able to say with much greater confidence not just whether El Nino was forming, but how strong it would ultimately become. Andrew Kruskivi, the Columbia University Climate Center scientist who had explained the spring barrier publicly, noted that the late May update would be the first forecast of the season that could be treated as a genuinely reliable guide to what the following autumn and winter would bring. For the Philippines, that meant the update would determine whether Pagas's existing El Nino alert needed to be upgraded to a higher warning level, triggering more aggressive government intervention in agricultural planning and disaster preparation. For India, it would determine whether the below-average monsoon forecast issued in May was going to hold or worsen. For Australia's farming sector, it would set the framework for water allocation decisions across the Murray-Darling Basin going into the critical late-year growing season. For Pacific Island nations with little buffer against extreme drought, it would determine how urgently to accelerate emergency food storage and water conservation measures. The update's significance extended beyond practical planning. Scientifically, a post-barrier confirmation of a super El Nino trajectory would shift the probability debate dramatically. The agencies that had been maintaining conservative outlooks would have to either confirm their skepticism with post-barrier data or revise upward. The European model's aggressive projection would either find support in the new data or begin to look like an outlier. Climate scientists watching the situation in May 2026 broadly expected the update to confirm a strong event at minimum. The debate was whether the data would support reclassifying the developing event as likely to reach super El Nino intensity. That answer, delivered with post-barrier confidence, would determine whether the preparations already underway across multiple continents were adequate or dangerously insufficient. But buried beneath all the probability numbers and agency projections was a question that rarely gets asked during the alarm phase of an event like this. What happens when the forecasters are wrong? 82% is not 100%, and in a world shaped by the 1 in 5 chance that gets ignored, that gap matters more than most people realise. Every probability statement released by every forecasting agency in May 2026 carried an implicit counterpart. NOAA's 82% chance of El Nino forming by July meant an 18% chance it would not. The 37% odds of a super El Nino by November meant 63% odds it would stay below that threshold. Even the European model's 100% projection carried uncertainty in its peak strength estimate. Scientists studying El Nino forecasting accuracy have documented a consistent pattern. Spring forecasts, issued before the predictability barrier ends, have historically overstated certainty in both directions. Events that looked certain have fizzled. Events that looked unlikely have exploded. The 2014 El Nino is the most instructive cautionary tale. In early 2014, subsurface heat content in the Pacific was running at exceptionally high levels. Kelvin waves were active, trade winds had weakened, forecasters at multiple agencies issued outlooks projecting a strong El Nino forming through the year. Some compared the setup to 1997. The event fizzled. Surface temperatures rose briefly into El Nino range and then retreated. The atmospheric response that drives a self-sustaining event never fully engaged. The heat reservoir, though large, dissipated without triggering the feedback loop that would have locked in a strong event. Scientists studying the 2014 failure afterward identified the atmospheric response as the key missing ingredient. The ocean was warm. The Kelvin waves had moved through, but the atmospheric circulation did not shift in a way that reinforced the warming. Without that reinforcement, the system could not sustain itself. In 2026, there were signs the atmospheric response was engaging. Westerly wind bursts were appearing. Trade winds were weakening. The surface temperature anomalies were spreading eastward across the Pacific. But all of those signs had been present in early 2014 as well, at least partially. The difference that scientists pointed to in 2026 was the scale and depth of the subsurface heat reservoir. In 2014, the heat content was high, but not exceptional. In 2026, it was at one of the largest values recorded at this stage of a development cycle. A larger reservoir meant more fuel available to sustain the event, even if the atmospheric response was incomplete. Australia's Bureau of Meteorology, the most conservative major agency, was retaining a meaningful probability of a neutral or weak outcome precisely because it weighted the 2014 analogue seriously. The uncertainty is real, the spring barrier is real. The possibility that this event develops at moderate rather than extreme strength is scientifically defensible, but the consequences of underestimating a super El Nino versus overestimating one are deeply asymmetric. Over-preparing for an event that turns out moderate costs money and effort, under-preparing for an event that turns out extreme cost lives, food security, and years of economic recovery. That asymmetry explains every alarm being raised in May 2026, and it leads directly to the question of what communities and countries can actually do when a signal this large is building in the ocean. Preparation for El Nino is not complicated. The hard part is doing it before the crisis arrives. Scientists who study disaster response have documented a consistent pattern across multiple El Nino events. Countries and communities that prepared before conditions deteriorated absorbed the damage far better than those that waited for visible signs of drought or flooding before acting. The margin between adequate preparation and catastrophic loss is often measured not in resources but in timing. Water is the first priority. During El Nino droughts, the single most damaging shortfall is water supply. Reservoirs that go into the dry season at full capacity can sustain communities and agriculture for months longer than those starting at partial levels. In regions where rainfall is expected to drop significantly, the weeks before a dry season begins represent the last opportunity to maximize water storage. In the Philippines, following the 2015 to 2016 event, the National Water Resources Board developed protocols for accelerating reservoir filling ahead of confirmed El Nino conditions. The 2026 El Nino alert triggered those protocols. Storage facilities were being filled to capacity in April and May before the main dry season arrived. Agricultural adaptation is the second critical layer. Farmers who switched to drought-resistant crop varieties adjust their planting schedules to front-load production before the dry season peaks, or shift to less water-intensive crops during El Nino years can protect significant portions of their income. Extension services in countries like the Philippines, India and Australia have developed crop advisory systems specifically for El Nino conditions, translating seasonal forecasts into farm-level guidance. Scientists confirm that these advisory systems work when they reach farmers early enough and communicate in accessible language. The challenge is the last mile, getting reliable, specific guidance to smallholder farmers in remote areas before planting decisions are locked in. Early food stockpiling by governments has historically been one of the highest return investments during El Nino preparation. Nations that build strategic food reserves before prices rise, rather than purchasing emergency supplies after they spike, pay substantially less and ensure supply more reliably. The World Food Programme confirmed this in its assessment of the 2015 to 2016 response across multiple countries. For coastal communities in Pacific Island nations, El Nino preparation intersects with the challenge of fresh water. Many small island communities rely on rainwater collection as their primary freshwater source. Extended droughts can deplete those systems within weeks. Pre-positioning water purification equipment and bottled water reserves, combined with community education on conservation, has prevented acute water crises during previous events. What does not work consistently is reactive preparation. Governments that waited for visible crop failure or confirmed reservoir shortfalls before mobilizing resources in 2015 and 2016 faced cascading crises that cost far more to manage than proactive preparation would have. The 2026 El Nino warning arrived earlier than any comparable event in the historical record. Forecasters gave governments and communities more lead time than they had before 1997, before 2015, before any of the 5 previous super events. Whether that lead time was used well would determine much of the human story of this event, but even with the best preparation, an El Nino eventually ends, and what comes after it can surprise communities just as badly as the event itself. The floods hit hardest after the drought ends. That sounds backwards, but for millions of people living in the Indo-Pacific, the years following a strong El Nino can be as dangerous and damaging as the event itself. The reason is La Niña. When El Nino reaches its peak and begins to decay, the Pacific does not simply return to neutral and stay there. The system tends to overshoot. The warm water that accumulated in the central and eastern Pacific eventually dissipates. Cold water surges back to the surface. Trade winds strengthen. The temperature balance tips in the opposite direction. La Niña replaces El Nino, and La Niña reverses almost everything El Nino did to regional weather. Regions that dried out under El Nino often flood under La Niña. Australia, which had been bracing for drought through 2026, would likely face above normal rainfall when La Niña arrived, potentially swinging from reservoir shortfalls to infrastructure-threatening floods in the same farming regions within 18 months. The Philippines and Southeast Asia, which suffered through El Nino drought, would see strengthened monsoon seasons and elevated typhoon activity during La Niña years. Scientists confirmed this swing pattern after studying the historical record of El Nino and La Niña pairs. The 1997 to 1998 El Nino was followed by a strong La Niña in 1998 to 2000. The drought regions of Asia flooded heavily. Australia's inland rivers ran high after years of below-average flow. Communities that had just rebuilt from El Nino damage faced a new crisis from the opposite direction. The 2015 to 2016 El Nino was followed by La Niña conditions that brought flooding and above-normal cyclone activity back to the Western Pacific. Eastern Australia saw significant flooding just years after the El Nino drought had stressed the same regions. For communities trying to plan over multi-year timescales, this oscillation creates a planning challenge that is genuinely difficult. Drought-proofing infrastructure is different from flood-proofing it. Agricultural systems optimized for dry conditions can be damaged by sudden excess rainfall. Water storage designed to hold maximum reserves against drought can overflow when La Niña delivers above normal precipitation. The scientific community has been consistent on this point. Preparing for El Nino without planning for the La Niña that follows leaves communities only half protected. The full cycle, typically 2 to 4 years from beginning of El Nino to end of La Niña, needs to be treated as a single event for planning purposes. Climate scientists studying the post-2026 Pacific outlook were already noting that a super El Nino of the strength being projected would likely generate an equally strong La Niña response. The bigger the warm event, the more energy it releases, and the more dramatically the system swings back in the cold direction. The Pacific is not just a thermometer, it is a pendulum, and when you push a pendulum this far in one direction, the swing back is not gentle. In 2026, scientists, governments, farmers and coastal communities around the world were watching the first half of that swing. They understood, with greater clarity than at any point in history, what was building in the depths of the Pacific. The question was whether that understanding would be enough to change what happened next. The ocean would answer that question on its own timeline, and it is already moving.